In this lesson, we will delve into Task 2.3 of Project 2 Precision Hole Machining Tools. In metal cutting processes, hole machining is a crucial component, and precision hole machining, in particular, demands extremely high accuracy. We will explore in detail the knowledge related to precision hole machining tools, including their types, characteristics, working principles, and applications in actual production. Additionally, by comparing the rough machining of drilling with the fine machining of boring, we will experience the transition from approximate to precise, fostering an engineering mindset that values precision and respects scientific principles. In the field of metal cutting, boring technology and precision hole machining tools play a crucial role. Precision hole machining is widely used in various industries such as aerospace, automotive manufacturing, and precision instruments. For instance, the various precision holes in aircraft engines, the holes in automotive engine blocks, and the hydraulic valves in construction vehicles. The machining accuracy of these holes directly affects the performance and quality of the products. The importance and characteristics of precision hole machining. Precision hole machining demands extremely high standards for dimensional accuracy, shape accuracy, and surface quality. Dimensional accuracy typically needs to be controlled within a range of a few micrometers or even smaller. Shape accuracy, such as cylindricity and roundness, also has strict standards. In terms of surface quality, a low surface roughness is required to ensure the fitting performance and service life of the parts. Compared to ordinary hole machining, precision hole machining requires more advanced tools and machining processes. Types and characteristics of precision hole machining tools. 1. Boring tools. Boring tools are one of the commonly used tools in precision hole machining. They can be divided into single-edged boring tools and double-edged boring tools. Single-edged boring tool. This tool has a simple structure, is easy to manufacture, and allows for convenient sharpening. Different cutting edge shapes can be ground according to various machining requirements. Its working principle involves cutting the whole wall with a single cutting edge. Single-edged boring tools are suitable for machining holes of various diameters and depths, especially for holes with high precision requirements and complex shapes. For example, when machining irregular holes on molds, a single-edged boring tool can meet the machining requirements through precise sharpening and adjustment. However, the cutting efficiency of a single-edged boring tool is relatively low because only one cutting edge is in operation. Double-edged boring tool. This tool features two symmetrical cutting edges that engage in cutting simultaneously, balancing the cutting forces and effectively reducing cutting vibrations. This enhances machining accuracy and surface quality. The working principle of a double-edged boring tool involves both cutting edges cutting the whole wall at the same time, effectively doubling the cutting efficiency compared to a single-edged boring tool. When machining large diameter precision holes, the advantages of double-edged boring tools become even more apparent. For instance, in the main bearing holes of automotive engine blocks, double-edged boring tools can complete the machining quickly and accurately. 2. Reamers. Reamers are primarily used for the fine machining of holes, achieving high dimensional accuracy and surface quality. Reamers can be categorized into straight flute reamers and spiral flute reamers. Straight flute reamer. This type of reamer is simple to manufacture and easy to sharpen, making it suitable for machining short holes and blind holes. Its cutting edges are straight, and during the machining process, the cutting force is primarily concentrated on the cutting edges. The working principle of a straight flute reamer involves multiple cutting edges, simultaneously performing minute cutting on the whole wall, gradually improving the dimensional accuracy and surface quality of the hole. For example, when machining holes in short shaft components with high precision requirements, straight flute reamers can be highly effective. Spiral flute reamer. This reamer provides smooth cutting and excellent chip evacuation, making it suitable for machining deep holes and through holes. The cutting edges of a spiral flute reamer are helical, which allows for a more even distribution of cutting forces during the machining process, effectively reducing cutting vibrations. Additionally, the spiral design facilitates chip removal, preventing chip clogging that could affect machining quality. For instance, when machining deep holes in aircraft engines, spiral flute reamers can effectively meet the machining requirements. 3. Floating boring tool. A floating boring tool is a special type of boring tool where the blade can freely float within the slot of the tool body. The working principle of a floating boring tool relies on cutting forces to automatically center the tool, which allows it to automatically compensate for tool installation errors and spindle runout errors of the machine. This ensures the dimensional accuracy and shape precision of the machined holes. Floating boring tools are suitable for machining large diameter precision holes. For example, when machining box holes in large machinery equipment, floating boring tools can effectively enhance machining accuracy. Selection and use of precision hole machining tools. When selecting tools for precision hole machining, several factors need to be considered. The first is the dimensional accuracy requirement of the hole. If the accuracy requirement is very high, tools with higher precision, such as high-precision boring tools or reamers, should be chosen. Secondly, the shape and depth of the hole are important. For irregular holes and deep holes, the appropriate type of tool should be selected. For instance, single-edged boring tools are suitable for irregular holes, while spiral flute reamers are suitable for deep holes. Additionally, the properties of the workpiece material will also affect the choice of tool. Different materials require different tool materials and geometric parameters. For example, when machining materials with higher hardness, tool materials with better hardness and wear resistance should be selected. When using precision hole machining tools, attention must be paid to the installation and adjustment of the tools. The tool must be installed so that its centerline coincides with the centerline of the machine spindle. Otherwise, machining accuracy will be affected. At the same time, it is important to reasonably adjust the cutting parameters of the tool according to the machining requirements, such as cutting speed, feed rate, and cutting depth. Excessively high cutting speed can lead to increased tool wear, while too low a speed can affect machining efficiency. A feed rate that is too large may result in a decline in surface quality, whereas a rate that is too small will increase machining time. Comparison of drilling rough machining and boring fine machining. Drilling is a common method for hole machining and is considered a rough machining process. The primary purpose of drilling is to create an approximate hole in the workpiece with relatively low precision requirements for the hole. During drilling, the cutting edges of the drill bit cut into the workpiece as it rotates. Due to factors such as the rigidity and guidance of the drill bit, the dimensional accuracy and shape precision of drilled holes are usually poor, and the surface roughness is relatively high. For example, in the machining of some standard mechanical parts, drilling is merely a preliminary pre-machining step. Boring, on the other hand, is a fine machining method that further processes the hole after drilling, enhancing the dimensional accuracy, shape precision, and surface quality of the hole. Boring uses a boring tool to precisely cut the hole wall, effectively correcting errors produced during drilling. During the boring process, through precise measurement and adjustment, the accuracy of the hole can be controlled within a very narrow range. For instance, in the manufacturing of aircraft engines, many critical holes require boring to meet high precision requirements. This transition from the approximate nature of drilling to the precise nature of boring fully demonstrates the central role of precision measurement and accurate adjustment in modern industry. In actual production, we must pay attention to every machining step and strive for precise machining results. which is a scientific mindset that we, as engineering professionals, should possess. Maintenance and care of precision hole machining tools. Precision hole machining tools are expensive and significantly impact machining accuracy, so proper maintenance and care are crucial. After use, tools should be promptly cleaned to remove chips and oil stains, preventing them from corroding the tools. Additionally, tools should be regularly sharpened and calibrated to ensure their cutting performance and accuracy. The storage of tools is also important. They should be kept in a dry, clean environment to avoid rust and damage. In this lesson, we conducted an in-depth study of Task 2.3 inches Project 2 Precision Hole Machining Tools. We first explored the importance and characteristics of precision hole machining, which demands extremely high dimensional accuracy, shape precision, and surface quality. We then introduced several common precision hole machining tools, including boring tools, single-edged and double-edged, reamers, straight flute and spiral flute, and floating boring tools, clarifying their respective characteristics, working principles, and applicable ranges. In terms of tool selection and use, it is essential to consider factors such as the accuracy, shape, and depth of the machined hole, as well as the workpiece material, while paying attention to the installation and adjustment of the tools. By comparing the rough machining of drilling with the fine machining of boring, we gained a profound understanding of the transition from approximate to precise, emphasizing the central role of precision measurement and accurate adjustment in modern industry, and fostering an engineering mindset that values precision and respects science. Finally, we also discussed the maintenance and care of precision hole machining tools, which are crucial for ensuring the performance and longevity of the tools. I hope everyone can further consolidate this knowledge after class, laying a solid foundation for future study and work.